Okay, so we are good to go. Just confirm I'm audible or not.
Yes, sir.
Great. So, welcome all to live session 4. What we will do today? So, today we will go through um, joining techniques like brazing, soldering, and resistance based joining techniques, right? So, we will go through. We will go through brazing, soldering, principles of these two processes, mechanisms, and then resistance based joining process like spot welding, seam welding, as you all know. And we will see that there is one numerical uh, based on this resistance based joining technique. We'll do that. Otherwise, other questions are from theory based only. So, the way we do, we'll go through the theories first, and in middle, maybe go through the questions first, right? So, let's start. Okay. So in brazing and soldering, mm, what we know, uh, basically over here, the surface which need to be joined, uh, you have to initially clean those surface. Maybe it should be fixture if anything needed. So over here, you will use a brazing flux or brazing alloy, right? So it will be a low melting point, non-ferrous metal. So brazing alloy will be a low melting point, non-ferrous metal, correct? Now, this metal will be drawn into the space which you will be creating between the two solids. So, if you want to join two different metals, it can be similar, it can be dissimilar based on your application. So, you usually do some edge preparation like V group preparation, and over here you will fill your groove with the braze filler, right? So this will be my brazing alloy, right? Now this brazed alloy is basically drawn into the two solids by something called capillary action. So I'm not explaining what is capillary action. This is well understood. So this is drawn into that space through capillary action, and then that is allowed to solidify, right? Now the composition or chemistry of the brazing alloy is it could be significantly different from the base metal, right? Now the strength of the brazing alloy is usually lower than the base metal, usually. So I will note it down. Strength of braze alloy is usually the strength of base metal, right? Now the melting point, as I was saying, the melting point of the brazing alloy is lower than that of the base metal. So over here in brazing or soldering, none of the base material will be melted, right? So the melting point is lower than base metal. Now the bonding will require capillary action to distribute your filler metal between the, so you have to fit your surface closely. So there will be some joint clearance. You have to provide some joint clearance. I will come to that. Due to capillary action, your filler metal will distribute in between those fitting surfaces, and that specific flow will depend on different properties, right? So there is viscosity of the liquid, there will be geometry of the joint, there will be surface wetting characteristics of the braze alloy. So those will affect your how the joining is taking place, right? Now, um, so of all those factors contributing to the, let's say, mechanical strength, I want to explore what is happening in braze metal joint strength. So joint clearance is the most important factor. Joint clearance is most important factor, right? Let's say if the joint is too tight, means the joint clearance is very small. It may be difficult for the braze metal to flow into the gap. Now, if it is difficult for the braze metal to flow into the gap, it will leave some unfilled voids. So the flux may not be able to escape, right? They will remain in those locations that should be filled with the braze metal, right? So there must be sufficient amount of clearance, or I will say optimum uh, clearance for the braze metal to wet the joint and flow into it under the force of capillary action, right? So it should not be too much tight, it should not be too high value, right? Now, as the gap, let's say the gap is increased beyond an optimum value, you have done some, uh, you have provided large amount of gap in between two solid metals. What will happen? So if the gap becomes too great, uh, the capillary force may not be able to draw those braze material into the joint or hold it into the place during solidification, right? Now, if I want to plot uh, mechanical strength in as a function of joint clearance, so let's say this is my joint clearance, and this is mechanical mechanical strength. Okay, how will it look like? How will it look like? So initially, till some joint clearance value, it will be increasing, and after certain value, you will see that the joint strength will remarkably decreasing with increase in joint clearance, right? So proper clearance should be chosen so that you will get some optimum value of mechanical strength, right? Now, it is also important to identify or to recognize that those clearance that should exist, what I am talking about, that is at the temperature of the brazing process. So this joint clearance, whenever you will design some joint, the clearance whatever you will consider during your design consideration, the joint clearance should be considered at the temperature where whatever is the melting point of your brazing alloy, right? So at brazing temperature, because always there will be coefficient of expansion or expansion contraction will take place because thermal expansion coefficient, right? So yeah, so any effects of thermal expansion that should be compensated when specifying those dimensions of the starting components or while you are considering your design for the joint, right? So this is particularly significant when you are joining dissimilar metal. So particular for dissimilar metal joining, right? Any question till now?
No, sir. Sir,
Okay.
but what's the main difference between soldering and brazing?
So it's mainly on the temperature part. So I will come to that. So for brazing, this is much more on higher temperature based process. Of course, it will not be more than the base metal melting temperature. You will work on something above 450. For soldering, the strength is very low. This is a low temperature melting point material. So it depends on material you are, which material or for what application you are doing the things. Yeah.
Sir, excuse me. Sir, strength means filler rod strength, right?
Yes.
Sir, in
Yes.
both process, filler rod is used.
Uh-huh. But feeler rod composition is different, right? So if you are talking about, let's say, lead or tin, the melting temperature for those materials is very low compared to if you are talking about nickel-based alloy or aluminum-based alloy or copper-based alloy, whatever is used for brazing. So the of course, you are using feeler material for both the process, but the application is different, the temperature is different, the material composition is also different.
Okay, sir.
Okay, so uh, yeah, let's consider a joint between brass and steel. So I was talking about this thermal expansion coefficient or what should be the joint clearance you should consider. So let's consider a joint between brass and steel. Okay, so which material will expand more, brass or steel, or which is having highest
Brass.
conduction? Right. So brass will expand more than steel when temperature will be increased, right? So if your design is such that, let's say you are doing some tube joining, right? So let's say you are joining something like this, and your inner tube is made of brass component. So let me take another. So let's say this is brass component, right? So if the insert tube is brass component, the initial fit should be somewhat a little bit loose because the brass will expand more than steel as the temperature will be increased and at the brazing temperature, right? So whenever you will consider the joint clearance, that should be compensated in your design. Conversely, if a steel tube is to be inserted into a, let's say, the external tube is made of brass and the inner tube is made of steel. So initially you have to do some force fitting, right? So if you want to insert the steel tube into a brass receiver and initial force fit should be required because interface will widen as brass expands more than the steel, right? So those aspects need to be compensated in your design. Now there are two more factors while you are considering brazing or soldering. So those two factors are, one is called wettability, another is called fluidity. By the name itself, this is more or less easy to understand, right? So wettability is kind of function of a surface tension, right? This is a function of surface tension between the base metal and the base alloy, of course. Generally, generally the wettability will be good when the surfaces are clean and the two metals can form some intermediate diffused alloy. So the diffusion coefficient will be very high for two different metals. The wettability will be good, right? Sometimes the wettability can be improved by some doing some coating. So let's say steel is sometimes tin plated to accept some uh, lead tin solder. So I'm talking about lead tin soldering. And if you want to do some soldering with lead tin solder, steel material is coated with tin to have some good wettability, right? Or it can be plated with nickel or copper based on your application to enhance this property. Now, what is fluidity? Fluidity is a measure of the flow characteristics, right? So, fluidity is basically show you how good is your brazed metal to flow into that uh, joint clearance. So, this is a function of temperature, joint clearance, and also surface roughness. So, fluidity is functional surface tension, temperature, and joint clearance, right? Right. Now, a good joint design is required uh, if you want to obtain adequate amount of mechanical strength, right? So the desired load carrying ability is usually obtained by assuring proper joint clearance, providing sufficient area of the bond. Now, in terms of design of those brazed joint, so what are different most commonly known joint geometry you have heard of? So there is lap joint, there is butt joint, right? So I'm talking about two different joint geometry. One is lap and one is butt. Now in butt joints, it does not require any additional thickness in the vicinity of the joint, or they're most often used when the strength requirement is not critical. So in your butt joint, because this is the area of the joint, right? The exposed area will be less. Now, in contrast, if you see lap joints, they can provide bonding areas. They will be considerably larger than what is there in butt configuration. You know? So lap joint area is much higher than the butt joint area, right? So if you're thinking of any application for your structural aspects, you should design your joint in such a way that they will be lap welded, not the butt welded, right? So that should be taken care of. Now there are different types of joint geometries also. So there is something called butt lap joint. There is something called scarf joint. Let me draw some pictures initially. So how does it look like, right? So give me some time. Um, in butt lap joint, it will look something like this. Something like this. These are my two different solid metals, right? And in scarf joint, it will look something like this. They will not be flat in nature, they'll be oblique. This is me, another metal. This is scarf joint, and this is butt lap, right? So this kind of design is an attempt to combine the advantage of uniform thickness with a large bonding area, right? So if you are doing this kind of design, you'll get the advantage of both whatever is there for lap and butt joint. So you will get uniform thickness in your joint, and you will have also the access in terms of large bonding area to get the load carrying capacity higher, right? The same concept is true for scarf joint also. So in scarf joint, it maintains uniform thickness and it increases bonding area by tilting the butt joint interface, right? So careful joint preparation, alignment, these things are required to maintain the desired clearance dimension throughout the length of those joints. Okay. Any question till now? The next
No,
question,
sir. But can you explain the real life applications of soldering and brazing?
a real life application for,
Soldering and brazing, nothing but welding.
yeah. So for soldering, mostly this is commonly used in electronics industry. So let's say if you want to manufacture and repair some, uh, let's say PCB, some printed circuit board or some other electronic components, where the exposure to temperature should be very limited, or some manufacturing of jewelry or some decorative items, small miniature items. There soldering is very necessary. Brazing is required for some thick metal sheet joining. It could be some 15 mm, 20 thick metals. If you are having some high temperature application, let's say for some nickel based alloy, some super alloy. I don't know these things you have heard or not. If for high temperature application. So in terms of high temperature application, it can be uh, some pressure vessel, so which will be require some pressure resistance, right? There will be requiring some leak proof joint. The joint should be leak proof in terms of pressure vessel, right? If
Okay, sir.
anything on automobile also, if your vehicle parts which should be corrosion free or it should be heat resistance, their brazing will come into picture. Okay.
Okay, sir.
Yeah. So next we come to feeder metal. Feeder metal for brazing. Next I will come to feeder metal for brazing. Now as I was saying, the filler metal used in brazing can be any kind of metal that melts between some around 450 and the melting point of the material that is being joined. So the temperature what you will be working on will be of course higher than 450 in brazing
450 degree centigrade, sir, or Kelvin?
degree degree. So most commonly used brazing metals are copper and its alloy, silver and its alloy, aluminum and its alloy, right? So many of the brazing metals are based on eutectic reactions. Do you remember what is eutectic reaction? Any guess? Yes or no?
No, sir.
Okay. So have you gone through in your metallurgy course or phase diagram course some binary alloy phase diagram in your metallurgy? Okay. Okay, let me explain. Let me explain. We'll be diverting a little bit, but fine. So if we talk about, let's say, are you familiar with phase diagram? At least you have heard of, right? Yes, no.
Yes, yes, sir. Yes, sir.
Yep. So let's say we're talking about some binary alloy phase diagram. So let's say two metals are there, A and B. So over here at left, it will be 100% A, 0% B. Am I right? As you are going towards right, it will be 100% B and 0% A. Correct? Now, how will it look like in binary alloy phase diagram? It will look something like this. There are some concepts called liquidus line, solidus line. I will not go into those aspects, but it will look something like this. So this is the melting temperature T melting for A. This is melting temperature T melting for B. This line, this is called liquidus line. This red colored line and this green colored line is called solidus line and blue colored line. This is called solvus line. Let's not go into what is liquidus, what is solvus. There is lot to explain over here. What I will talk about is this point. So eutectic reaction is a you can call it a three-phase reaction by which on cooling my liquid will transform into two solid phases at the same time at a constant temperature. So it will have some composition. This is my temperature. Let's say T eutectic. whenever you will cool a material, whenever you will cool a material, your liquid will transform into two different solids, right? So we call it alpha phase. Alpha phase is 100% A, 0% B. This is beta phase. Beta phase is 100% B, 0% A. So this can be true for different material combination, right? This can be true for, let's say, copper Fe. This can be true for copper aluminum. So always there will be some eutectic reaction that will take place, and that will be lower than the melting temperature of base metal, right? So liquid will transform into two different solids at a constant temperature, which is lower than the base metal melting. Little bit understood?
Yes, sir. Understood.
Yes. Okay. So as I was saying, uh, over here, this is based on many of the brazing methods are based on eutectic reaction. So here the material will be melted at a single temperature, which will be lower than the melting points of your individual metals in that alloy, right? Now, copper and copper alloys, they are mainly used for brazing steel or some high melting point materials, right? If you observe the melting temperature for copper, this is somewhere around 1080 degrees C. Now for steel, this is somewhere around 1400, 1500 degrees C, right? So if you want to braze steel material or some high melting point materials, this is desirable that you are using copper or its alloy, right? Now, unalloyed copper is usually used for some high speed steel or tungsten carbide material, right? Where you need some tight fitting of the joint. So let me note it down. Unalloyed copper. They are primarily used for high speed steel material or tungsten carbide material for some high temperature application. Now there is copper zinc alloys.
Sir, these are all the filler rods, right?
These are filler. Yeah. So
Okay.
I was talking about fillers only. These are our filler metals. Any confusion?
No, no, sir. Continue, continue. Yeah.
Yeah. So copper zinc alloys mainly used if you are interested for some low melting point applications, right? They are extensively used for brazing of cast iron or copper itself. So they are mainly used for cast iron or copper metal. So if you want to join copper or cast iron, copper zinc alloy can be used as your brazing metal. What else alloys can be used? There is copper phosphorus alloy. Copper phosphorus alloys are used for fluxless brazing. So fluxless brazing of copper because uh, phosphorus can reduce copper oxide film. Right? So these alloys should not be used with ferrous or nickel based materials because uh, as I was saying, phosphorus reduce copper oxide film, and also they form brittle compounds. So if you are working with this kind of alloy, copper phosphorus, the resulting weld strength will be less. So they will be brittle in nature. Okay. Then there is some alloy called copper nickel titanium. They mainly used to braze titanium and some of its alloy. Mainly used for titanium. Okay. So except copper and copper alloys, I was talking about silver. So pure silvers can also be used for titanium. Okay. Then there is also silver solders. So their alloy is based on silver and copper, right? They have brazing temperature significantly below that of pure copper, and they are also used in joining for steel, copper, nickel, this kind of metals, right? Next, you have aluminum alloys. So there is aluminum silicon alloy. Now, in aluminum silicon alloy, mainly 6 to 12% of silicon is mixed with aluminum, and they are used for brazing of aluminum and other aluminum alloys, right? So by using a brazed metal uh, that is similar to a base metal. So if your brazed metal and your base metal are similar, what will happen in terms of corrosion? The possibility of corrosion will be reduced, right? If you're doing some dissimilar metal joining, there will be something called galvanic corrosion. The corrosion tendency will be huge, right? So corrosion tendency will be reduced. Next, there is also nickel and cobalt based alloy. They're attractive for joining some assemblies that will be subjected to some elevated temperature service condition or some extremely corrosive environments, right? Right. Now, if you see these filler metals, they are primarily available in the form of some amorphous foils. Have you seen any brazing filler metal? They mainly are available in terms of amorphous foils, right? So they are formed by cooling the metal, and the cooling will be extremely at a rapid rate. So these foils are extremely thin, maybe um, in the range of some 0.0015 inch or some point 0.3205 mm, 0.03 to 0.04. I'm not sure, but in the order of that range. And they will exhibit excellent ductility and flexibility even when they are made from alloys or crystalline form is quite brittle, right? So mainly they are available in terms of amorphous foils. Okay, so these are few brazed filler metals which is generally used in industry in research purposes also. Question? If no, so then I will move to brazing flux. What is brazing flux? Any idea?
Sir, during the welding processes,
Mhm.
some amount of like I didn't know that, sir, but I know that.
So in welding, we talk about flux coating, right? In shielded metal arc, it's mainly for protection purpose. You will form some
Yes, sir.
slag.
It it forms like a shielded, sir, blanket like.
Mhm. Right, right. So over here also, it has some purpose. So in normal atmosphere, the heat required to melt the brazing alloy that will cause the formation of some oxide formation, right? There will be some surface oxide formation, which will always restrict the wetting of the surface and subsequent bonding. So brazing flux will play a role by dissolving those oxides that might be forming on the surface prior to heating, by preventing the formation of those new oxides during heating, and also uh, it will reduce the surface tension between the molten base metal and the surface to be joined. So it will basically promote the flow of the molten metal into the joiner. So ideally what is happening? The flux is getting melted and it will become active at a temperature below the uh, I was talking about solidus. So again, below the solidus temperature, it will be completely solidified. So if this is liquidus temperature, if this is solidus temperature, below the solidus temperature, it will completely solidify, right? So, okay, let me write it down. So I was talking about dissolving the oxides. I was talking about preventing formation of new oxides. I was talking about lowering the surface tension, right? So over here, surface cleanliness is one of the most significant factor that will be affecting the quality and uniformity of your brace joint, right? So before a flux is applied, you always have to remove the dirt or grease or oil, rust if anything is there. Those need to be removed from the surface, from the metal surface that you want to join, right? So there are different procedures of how we want to clean it up. There is some water or solvent based technique. There are some high temperature burn off, scratching, grit blasting. So there are many techniques by which you can clean your surface, right? Now, brazing fluxes usually take the form of chemical compounds in which most common ingredients are. Any idea what are most common brazing fluxes we use? So there is borax, There are some chemical compounds mainly used. Fused borax, then some fluoride, some chloride. These are mainly used as brazing classes, right? Some alkalis also. And also, your flask should be selected for compatibility with your base metal being brazed, right? And the particular process that is being used. Now, how you should apply your brazed metal, or how the process is done. Hmm? There is something called torch brazing. I have. Okay, why don't we choose some question and answer first? Then we'll come again to the theory part. So let's solve question one. It asks it asks me, in the process of brazing, the filler metal is drawn into the metal by means of this. Which one should be correct? We have already
I
discussed.
think capillary action or suppression sensor.
So capillary action is the primary mechanism, yes. Surface tension also plays a role, but if it is multiple choice, yeah, A and B both are true, but primarily D is the most correct option. A is correct. The commonly used flux in brazing.
Borax.
Correct. How does the strength of a brazed joint change with increase in clearance? So I have shown you the graph. So initially strength increases and then decreases. I still not have come to soldering. I will come to this part. Question 4. Okay. Next everything. 4 and 5 is from soldering. Which of the following is true for brazing? Question 6.
All of these, sir.
Over here, all of these are true. Hmm. Okay. These are simple questions, right? So,
Yes,
yeah.
sir.
So I was talking about the method how you should apply your brazed metal. I was talking about something called torch brazing. So over here, the technique, this uses a brazing metal in the form of a rod or wire, as you were saying, the filler rod. So over here, the joint area is first heated to a temperature high enough to melt your braze alloy, and will ensure that it remains molten while it will be flowing into the joint, right? So the torch is then used to melt the braze metal, and uh, because of capillary action, it will be drawn into that gap, right? However, this torch brazing is labor intensive, right? So care must be taken to ensure that uh, your feeder metal has flowed into the inner portion of your joint. To avoid that difficulty, uh, to avoid that difficulty, your brace or the filler metal is kind of prior to heating, it is usually in the form of some powders or some disc or slugs or some foils, right? Uh, so capillary action will always pull your molten base metal into the smallest clearance. So depending on your joint clearance, whatever is there, capillary action will always pull your molten base metal into the smallest clearance, regardless of whether that was your intended location or not, right? So that should be taken care of. You have to ensure that the filler metal is not drawn away from your intended surface by the capillary action, right? Right. There is some another approach, some kind of dipping or coating your surface, coating your metal surface that you want to join with braze alloy. So simply placing the material in contact and uh, heating towards desired temperature, right? So I was talking about torch brazing, dipping, coating. So these are some procedures through which you can apply your filler metal, and then sufficient amount of heat to be generated over there to melt your brazing metal, brazing filler and brazing flux as well, right? Right, right. So this I was talking about um, application of or procedure to apply filler, right? Now, how you should heat your how you should heat your braze metal, or what should be some uh, heating source? So torch brazing, as I was saying. So mainly this is a gas flame combination. We have talked about gas welding. So there is oxyacetylene, oxyhydrogen, and different gas flame combination can be used to heat up the metal. Now, local heating is the best option where that will permit the retention of most of the original material strength, and it will enable large components to be joined with little bit of distortion, right? So if you can somehow heat your metal very locally, that will be the best option in your braze welding technique, right? So local heating, torch brazing. Now in major drawback, what can be the drawback for local heating? There can be difficulty in controlling the temperature and maintaining uniformity of heating in if you are doing some heating locally, right? Then there is furnace brazing also. This we call fluxless brazing. This is also called fluxless brazing. Okay, because you are doing it in a vacuum furnace, no need to use flux for protection of your oxide films or the oxide formation over the surface. Vacuum can take care of. So this is called fluxless brazing. Then also there is something called salt bath. So over here, the salt will act as the brazing flux that will prevent your oxidation and it will enhance your wettability, fluidity, whatever is there. Uh, the work will heat up very rapidly because it will be in complete contact with the heating medium. So this will be into the bath. Over here, temperature can also be accurately controlled. So thin pieces can be attached to thicker pieces. So you can do brazing of different thickness combinations also. Then you have, I was talking about deep brazing. We also can have induction brazing. So local heating and induction brazing is similar thing. Why people join now? Fine. So yeah, I was talking about induction brazing. So that utilizes some, as you know, in induction it utilizes some high frequency induction current, right, as the source of heat, and it will be limited. The main disadvantage, it will be limited to the joining of electrically conductive materials, right? However, the complete heating cycle will be very rapid, usually only few seconds of duration. The operation can be semi-automatic. Heating can be confined to a specific area of the joint. So those advantages are there also in terms of induction brazing. There is resistance brazing also. Okay, these are some heating source in your brazing thing. Okay, okay. Now let's come to the soldering part. Till now, any question? Okay, sorry. So, as I was saying, soldering. So, in soldering, the filler metal, what we'll be working with, the melting temperature of that filler metal will be below 450. So, for brazing, it will be above 450. For soldering, it will be below 450. It is typically used for joining thin metals, as I was saying, connecting electronic components, right? Joining metals when you want to avoid exposure to high elevated temperatures, or if you want to feel some surface flaws, some defects, some miniature components, right? Now over here also there are different designs through which you can increase your joining area. You can always think of how you can increase your joining area so that it can bear more amount of load, right? So there is uh, ठीक है, I will just draw the cross section and then I will name for those designs. So this is called flanged butt joint, through which you can increase your surface or contact surface area a little bit. Then there is some flash lamp lap welding. This is called flush lap joint. Then you can have flanged edge joint. So these are some joint preparation. You can have some interlock kind of thing, right? So through which you can also increase your joint area. But of course, to prepare this kind of joint geometry is complicated. Now, yeah, now low joining temperatures are mainly used for heat sensitive materials, right? So solder joints are often developed for shear strengths in excess of some 1.5 MPa, right? So it is appreciable that whenever you whenever your application is not structural specific, or you don't want your strength too much, like in electronic component, the main objective is the current flow, right? So the electrical resistance should be lower. The structural aspect is less in electronics. So over there, soldering is suitable. If you want to go for some structural application, then you go for brazing application. Got it? Now, in soldering, uh, they are generally combination, the soldering alloys, they are generally combination of low melting temperature metals such as lead, tin, bismuth, indium. So lead, tin, indium, cadmium, silver. So all low temperature metals are generally, you can do some combination of course, generally used as soldering alloys because of their low cost, low melting temperatures, and yeah, they are most common solders, right? Most commonly used is lead and tin. The alloy of lead and tin is most commonly used in soldering aspects. Here also most of the alternative solders which have been proposed, they're from other eutectic alloy systems. So I have talked about eutectic. Now there can be tin antimony alloy or tin copper alloy. So people are developing these alloys which you can use in soldering, which can be useful in electronic application, and they will have a certain amount of good strength and creep resistance. Uh, but let's say for copper tin, because you are mixing copper whose melting temperature is higher than whenever you are mixing lead with tin, they will be used for some high temperature application. Okay. Now, in terms of soldering flux, so I was talking about brazing flux, there is soldering flux also. So they are generally classified as corrosive or non-corrosive. So most common non-corrosive flux is corrosive or non-corrosive. What is the more commonly used non-corrosive flux? This is called as rosin, right? This can be dissolved in alcohol. Rosin dissolved in alcohol. So rosin fluxes are suitable for making joints to copper, brass, tin, cadmium, those metal surfaces, provided surfaces have been adequately cleaned prior to soldering, right? Then you have aniline phosphate. That is also some active non-corrosive flux, but it has limited use because uh, it emits some toxic gases when heated. Okay, leave it. So these are some fluxes which is used for soldering fluxes. If now in terms of operation, I want to mention uh, few names. I want to mention a few names. One is called vapor phase soldering. You can go through these names: vapor phase soldering and deep soldering. So something called wave soldering. Okay, these are few different procedures of doing soldering method. Now in wave soldering, the molten solder is pumped upward through some nozzle to create a wave. Basically, it is a pool of molten metal, and it's mainly used in PCB, printed circuit board. So the printed circuit boards are passed across this wave at a height, and so each of the pins is contact with the molten metal, right? So it is something like this. So I'm a little bit diverting, but yes, just remember these names. There will be a pump which will create a wave, something like this. This is all molten metal flow over here, and so let's say this is my printed circuit board, right? It will be, and there can be some flow control baffles also. There can be baffles also to control your flow, and there will be contact between this flow of molten metal and this pin of the PCB. This is how it happened in web soldering. Okay, we'll leave it. Can I quickly go through this question 4 and 5? Then we'll come to the resistance welding part. Hmm? So soldering is an alloy of commonly. Commonly soldering is an alloy of what? Hmm? Question 4, option C. Yeah. So C is correct. Then soldering process is carried out in temperature range of the range what I have provided here a little bit different of what I was talking about. But yeah, what is the range? So mainly in soldering,
Sir, you said
we work
450
with.
like
Sorry, I continue.
the temperature is 450 like that. Is it braising or soldering?
So for brazing, this is let me mention for brazing, this is greater than 450. For soldering, it can vary depending on your material combination. Okay, so this is a generalized temperature range. Okay, okay. So next we'll come to the resistance welding part. Lot of brazing, soldering thing done. Yeah, we have some space over here. Okay. So how is heating done in resistance welding? In resistance welding, how is heating often? So you'll pass some large electrical current through the workpiece for a short period of time, right? So, so total heat input that will be going into the material that will be I square RT, right? So the joule heating is happening over here. This is well known, right? So if we see a resistance spot welding machine, what you will have, you will have some pressure cylinder, some pneumatic pressure cylinder through which we will control the pressure of the electrode. This will be workpiece. This is electrode, and these two electrodes will be connected to a transformer.
Sir, this is spot welding, right?
Yeah,
Okay.
something like this. So what do we have? You have a bulk resistance of the electrode and workpiece. So I will have bulk resistance of the electrode as well as of the workpiece. So you have upper electrode, upper workpiece, lower electrode, lower workpiece, right? What else you have? You have contact resistance also, right? You have electrical contact resistance. Resistance between the same surface, right? How the temperature will evolve or how will it look like? Let's say this is my electrode. Let me look this up. If this is my electrode and this is my workpiece, and over here I am forming this nugget, my temperature will look something like this. So it will increase, then it will increase more, then it will something like this. Right? And these electrodes also will apply some forging action. Is it not? Because uh, this applied pressure that will promote your forging action, resistance welds can be produced at lower temperatures also than the welds made by other process. Right? Now, controlling both the magnitude and timing of this pressure, that is very crucial in resistance spot welding. If too little pressure is used, what will happen? The contact resistance will be high, right? And there will be some surface burning or pitting of the electrodes that may result. If excessive pressure is applied, what will happen? The material will, the molten metal volume will be higher, right? If excessive pressure is applied, the metal will get softened or it will get melted very quickly. And what will happen? The melt material can be expelled from the faint surfaces. है ना? So pressure control, pressure and time control is crucial. What is this time called? You've heard of squeeze time, right? This time. Now, if I want to plot a graph in terms of current and the pressure, how will it look like? So let's say this is time and this is my current or pressure. So initially I need high amount of current and during that time my pressure will be less. So this is my pressure. And after that, I will increase my pressure, the forging pressure, for sufficient amount of time. And during that time, I will reduce my current. So the blue one is current, the hashed one is current, and black one is pressure. Why this is something like this? So my resistance will keep on changing as the current will flow and as the material will get heated, right? The bulk resistance of metal that will increase as the temperature will rise up, है ना? So bulk resistance of the material will increase as temperature gets increased. What about the contact resistance? Contact resistance will decrease because you are applying pressure. As you are applying pressure, the contact area is getting initiated. It will get increased. And for that reason, contact resistance with time will get reduced. right? So the initially my contact resistance will be much higher, and at that point of time, high currents and short time intervals are generally preferred. So this is my initial period of time when I need high amount of current, high pulses, because at that point of time, contact resistance is very high, so the heating will be very high. Whenever I approach towards the almost the melting temperature, then I will reduce my current and I will apply my forging action through pressure. What is this called? This is squeezing time. Question: what can be the current range in uh, for the power supply in spot welding? Any idea?
Sir,
What will be the range of your power supply current in spot welding? This will be in
no, sir.
kiloampere range. So it can be as high as 100 kiloampere, because the overall resistance in your welding circuit, that will be quite low. That's why high current is required to produce a resistance weld. So that's why power transformers are used. So the transformer will convert the high voltage low current line power to the high current low voltage. No? So let me write it this also. In general, what is the voltage of your main supply? Can be 230 volt. It can be either single phase, three phase. Mainly for higher power demand, generally three phase AC power supply is used. So high voltage, low current is getting converted to low voltage. This is as low as 5 to 10 volt. I'm not sure, but yeah, low voltage and high current. This is as high as 50 to 100 kiloampere. So we talk about spot welding. What are different resistance welding? There is spot welding, there is seam welding also. I'm not going into detail of the spot and seam welding again. Anyhow, these are well known. Now, in terms of electrode materials, so your resistance spot welding electrodes must conduct the welding current to the work, right? So you set your current density at the weld location, you apply force, and you help the heat to dissipate during the non-current portion of the welding cycle, right? So electrical and thermal conductivity properties are important consideration for your electrode selection. Also, so for electrodes, so I'm also mentioning few answers of the questions what I provided over here, so that it will be quick. So for electrodes, what properties I need? Good electrical and thermal property, and good hot compressive strength. Otherwise, it will get wear out because you are applying pressure and it is getting heated. Correct? Any question till now?
No, sir. Go ahead.
Hmm. Okay. So as I was saying, in seam welding, the weld is made between some overlapping sheets of metal. Seam is basically or simply that will be a series of overlapping spot welds. Right? The exception is that the electrode will now assume in the form of some rotating disc. So in seam welding, it will happen in terms of a rotating disc. It will not be a cylindrical electrode. Then there is something also called projection welding. I forgot to mention. Projection welding is also there, right? So in a mass production operation, basically small electrodes provide both the high currents and the required pressure. Uh, the electrodes can get wear out, right? And also, spot welding is mainly used to prepare one spot weld at a time, right? If you want to increase the strength, what do you need? You need some overlapping area, or you need to increase your area. So these limitations are overcome by this projection welding. There will be a dimple which will be imposed into one of the workpiece, and basically somehow you are increasing the resistance so that the temperature will be higher, and you can do multiple spots at a go for projection welding. Okay, so finally, uh, we have a numerical from spot welding, and then we will wrap it up. So if you do not have any question, let's try the numerical. This is a little bit lengthy, but in terms of conceptually, this should be simple enough. So just go through the question once. So here I say resistance spot welding of two steel sheets is carried out in lap joint configuration. I have my welding current is given as 3000 amp. Time is given as 0.2 second. Weld volume, that is given as 20 mm cube. Effective resistance is given as 200 micron, and there are few properties are provided for steel material. We need to calculate a heat transfer efficiency. How you can calculate heat transfer efficiency? So there will be some amount of heat which is getting generated. There will be some amount of heat which will be actually required to melt the material, right? That is my efficiency. So what is the heat that is getting generated for spot welding is I square RT. Can you quickly calculate how much joule is this? So this is 3000 square into 200 into 10 to the power minus 6 into 0.2. This much of Joule. Are you guys calculating? From next day onwards, if you don't have calculator as of now, that is fine. From next day onwards, keep the calculator with you. Are you guys calculating it now? If you're calculating, then I'm waiting. Hello? Am I audible?
Yes, sir.
Yeah. Thank you.
A 360 joule, sir. Heat.
Is it coming 360 joule?
Yes, sir.
Okay. Great. So this is heat getting generated due to the electrical resistance. Now, what is the actual heat that is required for melting? Now we can calculate that. So it is provided latent heat of melting is this, density this, melting temperature this, specific heat this. The heat required for melting is what? mCp plus, if you are considering the latent heat of fusion, this is plus ml. This is basic physics, right? So m into cpdt plus L. What is m? M is rho into volume. So rho is provided. Density is 8000 kg per meter cube. 8000 kg per meter cube. This is 20 cube. Weld volume is provided as 20 cube. So 20 into 10 to the power minus 9 if you are converting it in meter cube. So this is my m, that into that into this is 0.5 kilojoule per kg degree C. So 0.5 into 1000, 500, that will be in joule. Please ask me if it is not understood. 500 into dt. dt is how much? Melting temperature is 1520, ambient temperature is 20. So dt is this. So this is Cp dt plus latent heat of fusion is 1400. So 1400 E3. This is in joule. Am I right? So can you please quickly calculate this? How much?
ये लास्ट टर्म सर 1400 into e की पावर 3 है.
This one?
ये लास्ट
1400,
500. हाँ
1400 into 1000. E3 means that will be multiplied with 1000.
एस की पावर 3.
Yes.
ओके ओके सर. 1400 into 10 to the power 9.
Hmm?
1400 into 10 to the power 9.
This is too much. Still consider 10 to the power minus 9 over here.
Yes, sir.
Oh. Should I check once?
एक मिनट बेटा मैं क्लास चल रही है.
Let me check once.
It required more time, sir.
Let me check once.
At this time, calculator not available.
No problem. Let me check once.
Oh,
This into so for me, this is coming as 344 joule. So just check with your calculator if it is coming or not. This should come. Uh, what you were telling is very high value,
yes, sir.
right? Anyhow, so if it required for melting is 344, if it is getting generated is 360, my efficiency will be 344 by 360. This into 100, this much of percent. This is coming as 95.5. So somewhere around 96. So my transfer efficiency is 96%. Understood?
Yes, sir.
Okay. So is there any question?
No, sir. I
Okay.
will try this question. Okay, sir.
Yeah, sure. So in our earlier lecture video, I provided the mail ID. So
Okay, sir. But sir, is question number 7th, 8th, 9th.
I missed, no? I missed this. Sorry. So the value of welding current required to successfully weld in resistance spot welding depends upon, it's simple, thickness of the sheet, electrical conductivity, number of spots, this,
All
and
are
this,
B.
right?
Okay, sir. Question number
Number of
6 also, sir. Question number 6 all are B. 6 also similar all are B. Okay, sir.
so number of spot welds also will affect your spot welding electrical resistance. Right? So let's say you are joining two metals, you have one spot weld already made. Now you want to apply pressure and create a spot over here. Will there any change in your resistance? Because current will flow from here, and because you have created contact at this area, current will try to flow through this area, right? Contact resistance will be lower over here. So when you want to join at a different location, you have to apply higher amount of current.
Okay, sir.
Next, which of the following is true about electrodes? This will require low electrical conductivity, low mechanical strength. No, no, no. So my electrode should be as I was saying over here,
Sir.
where this one.
Okay.
So my electrode will be high electrical conductivity and high mechanical strength.
Yes, sir.
Now the shape of the resistance welding electrode, that will also matter. Which
Heavy
will
load.
which will be suitable for heavy load and severe heating. If you have a flat T, so let me do this.
Dome shape.
Right. So dome shape will be suitable for heavy load and severe heating because the current density. Let's say if you are having a flat surface, if you are having a cone surface, and if you are having a dome shaped surface, the current will be much more concentrated over here. The current density will be much higher compared to what you will get for other two geometry because current
Flat tape.
density.
A
Yeah,
flat tape also, I think, correct.
sorry,
Correct option is dome shaped or flat tape.
correct option is dome shape because,
Okay, okay, sir.
yeah, let's say if you're having a flat electrode area, let's say you are having area is A and current is I. Okay, what will be the current density? Current density will be I by A. So as you will be lowering the surface area, you will be increasing the current density. As you will be increasing the current density, there will be more heating to your workpiece. Got it?
Yes. Okay, sir. Okay.
Yeah. Okay. So we'll meet
Okay.
next week again.
Yes, sir.
Yeah.
Thank you,
Bye
sir.
bye. Thank you.